Let's get started, please, JM.
Okay, welcome back. So I spent most of yesterday's lecture motivating this problem of tensors and minimal border rank. The motivation came from the complexity of matrix multiplication. And I didn't quite get to finish last talk, so I'll finish last talk and then I'll start today's talk. So recall that we had discussed 3 tests for minimal border rank, one from 1983 through the Strawson, one from 2014 with Taviani, and then I want to review this one because I went too fast. So if you have a tensor, you can look at its symmetry group. Those are the changes of bases that do nothing to your tensor. And if you take a random tensor, it will have essentially a trivial symmetry group. But if you have a very special tensor, it will have a non-zero symmetry group. For purposes of computation, as in always in mathematics, it's easier to work infinitesimally. So we look at instead the infinitesimal symmetries, that is to say its symmetry Lie algebra. So the group would be like G1, G2, G3, such that when I hit it with T, nothing happens, I still get T. But when I differentiate that, if you differentiate a constant, you get 0, and this is the equation you get. And this is respects degeneration in some sense. So for example, if I take our friend the unit tensor, which should be on the board, I guess. I take this unit tensor. And if I rescale A by 7, I rescale B by 3, and I rescale C by 1/21, this whole thing, nothing will happen. Or, sorry, no, minus 10, because it's infinite. See, addition is much easier than multiplication. So I just need to rescale these by something that sums to 0. And then it'll be killed. And in particular, this group has dimension 2m. So if this respects degeneration, the dimension of this group, this symmetry Lie algebra. So if the border rank is less than or equal to m, then the symmetry Lie algebra must have dimension at least 2m. And that means this system of linear equations must have at least a 2m dimensional solution. So that's a bunch of equations on a vector space of dimension 3m squared, must have at least 2m solutions if my tensor has minimal border rank. Question? It's okay? So this is a polynomial condition based on the rank of some 3m squared by something by m cubed matrix. Okay. So this is not so important for my talk, but this is maybe more familiar compared to what I'm going to introduce next. And this is going to be sort of the surprise of this lecture. So this 1-1-1 algebra, or centroid of our tensor, it's not quite like the Lie algebra where we wanted x hitting t plus y hitting t plus z hitting t equal to 0. Here we want x hitting t gives the same answer as y hitting t, gives the same answer as z hitting t. And at first, this may seem like a strange object. Originally, we called it the 1-1-1 space, because it was known by the Baczynski family that that space had to have a certain dimension. But our contribution was to realize that that space was not just a vector space of solutions, but it had the algebraic structure. If I have two things in here, and I can take their composition, it'll still be in. If I add them together, it's still in. That's clear. The composition is the subtle bit, and it's an abelian Lie algebra, which is even more surprising. So for example, with our unit tensor, then we just get the diagonal matrices repeated 3 times, and it's pretty clear that if I multiply A1 by mu1, that's the same thing as multiplying B1 by mu1, because I could pull out my scalars. This object turns out to have remarkable properties for us. So it's not entirely obvious, but it's true that if my tensor is concise with minimal border rank, it's 1-1-1 algebra as dimension at least m. And what I want to discuss, what I'm hoping to discuss today, is that this will give structure to a class of tensors that were previously not known to have any structure. Okay, so let me remind you, there's this laser method, and again, we have this world champion tensor. This top line looks like 3 different 1, 1n matrix multiplications. The bottom line is a little mysterious, but I assure you this is the world champions since 1988. And I remind you that it's subject to limit. It's never going to prove the exponent is 2.3 in the laser method. And there's a geometric explanation why it's not going to, because this quantity we discussed last time, the asymptotic subrank, is small. That's from review of last lecture yesterday, a long time ago. Good. And so this, like I said, this gave rise to a general geometric test for maximum possible utility of a tensor in the laser method. So if I remember, we can view a tensor as a space of matrices whose entries are linear forms. And if I take this world champion Coppersmith-Vinograd tensor and I write it as a space of matrices, it has this structure. So there's like a linear form on the diagonal repeated, and then there's all these are different linear forms, and then I repeat going down, it has this structure. And now comes the punchline of yesterday's talk. I give it to you today. Here's a new tensor. It looks just like that one, except I added the blue. There were zeros there, and I stuck some non-zero stuff in. And in fact, just like the Coppersmith-Vinograd tensor, this tensor has minimal border rank. So there are 2 things we were hoping for. It is minimal border rank and asymptotic subrank as large as possible for the laser method. And the theorem is that we name it better because it is better. It's better than the Coppersmith-Vinograd tensor for Strawson's laser method in the following sense, that it degenerates to Coppersmith-Vinograd. That means it's at least as good because the cost is the same and the value is at least as good in the laser method. But why is it better? It's better because its asymptotic subrank is strictly larger than the asymptotic subrank of the Coppersmith-Vinograd tensor. And this says that it's subject to a weaker barrier. Now, if I were giving this talk in June, hopefully I would then give you a new upper bound on exponent of matrix multiplication. This, you notice it's February 2025. So this tensor is only a few weeks old. Well, of course, it's been around for all eternity, but we've only known about it for a few weeks. And we gave it to our friends who are world experts in using Strawson's laser method, and they they, for their own reasons, agree that it should be able to beat Cup-Smith integrated tensor, but they haven't gotten there yet. But the year is young. So that was going to be the punchline of last talk. So it'll be the punchline of today's talk. And now in this lecture, I want to explain where this thing came from because it looks like a rabbit out of a hat. And this actually came from a very systematic and geometric study. This thing it's not like we're really smart and we thought, oh, let's look for something like this. The geometry guided us to this tensor. So I want to explain how the geometry led us to this tensor. But first, I would like to give you, maybe you could care less about matrix multiplication. So I want to give you, please.
So what, this represents which tensor? So I don't understand the representation you are using here.
Yes?
So what is it? So you have a...
So wait, let's go back. Do you understand this?
No.
Okay. So you understand this?
Yeah.
Yes? Okay. So now look, I have this A0 and I have, let's look at this one. Yeah, I have A0 and then I have B1, C1, B2, C2, B3, C3, etc. That's this thing. This is like playing the role of the A0.
And the H are function of...
Yeah, H is A0. And then I split up my variables because of what's coming next, not because of this. I changed variables. And then this, so that I explained to you this term. Well, it's actually this term plus this term, to be more careful. And then let me explain you this term. That's this line across here. Then this term is this vertical thing going down here, except the 3 corner points. And the 3 corner points are these 3 extra terms that gave me the other stuff.
yes.
Yeah. So I slightly changed notation because of what's coming next. And that's the winner. So that winner has these extra terms. If I wrote it as a tensor, it'd be this CW6 plus 6 additional terms, or 3 additional terms.
Okay. So you represent the slices somehow?
Yes.
With
yes, exactly. So H is the first slice, G1 is the second slice, G2 is the third slice. So just set H equal to 1, all the rest to 0, that's the first slice. Set G1 equal to 1, all the rest equal to 0, that's the second slice, etc. Okay. So I'm presenting all the slices at once. I'm giving them funny names because of what's going to come later in the talk.
What is that explicit tensor of largest known border?
What?
What is the kind of the champion tensors of this size that has the largest border rank? This one.
No, border rank. We don't want border rank.
You want subrank?
Largest asymptotic subrank.
Largest tensor.
Well, but that would be the unit tensor.
Okay.
But I'll explain in a moment, the unit tensor is useless for laser method.
Okay.
And so there's a part of the laser method that I didn't discuss properly. I hinted at that you want to be able to present your tensor in a way that it looks like it has these tiny matrix multiplication tensors. And that's kind of, so this is the world champion so far in what's been proven, and this is our candidate for the new world champion. Okay, so, but maybe you could care less about matrix multiplication, so I want to give 2 additional motivations for studying tensors of minimal border rank. So if you were lost here, that's great because we're starting over now with a completely new topic. So I want to talk about a problem in algebraic geometry or representation theory that appears many times. It's a beautiful question in and of its own right. So let's take a vector space. Let's take a group, a subgroup of the group of changes of bases. Reductive, in the language of Giorgio's talk, is if I have a representation of the group, it always decomposes into a direct sum of irreducible representations. That's not important for this talk, but I put the word up for those who care about it. And many of the groups you like are reductive. the group that you like that's not reductive is the group of invertible upper triangular matrices. That's the, so reductive is like the opposite of solvable. So I want to consider the orbit closure of my vector, or I work in projective space. And
I think it's the opposite of nilpotent.
Well, whatever. I mean,
Okay, but I see what you mean.
so, well, so I almost talked on a completely different subject where the whole lecture series would have been on Borel subgroups. But I changed my mind because I was told not to use representation theory. This talk has almost no representation theory. It has no representation theory other than this slide and the next. So the point is I have an orbit closure, and what's interesting is what goes on the boundary. So let's give some examples to convince you that this is an interesting question. So first, let's take the space of matrices, our group change of bases, and our matrix will be look like the identity and then padded by zeros. Kind of the simplest thing you could think of. And I meant to ask you, what is its orbit closure? So I take the matrix.
All space.
No, I take a matrix that looks like this, 1, 1, and then zeros everywhere else. There's R at these. What is its orbit closure? Or what is the boundary?
Rank equal to R.
That's totally wrong,
No.
Professor Ottaviani.
Is that?
What is the
boundary is strictly smaller than.
what is the boundary?
Strictly smaller than.
Good. Yeah. The boundary is the set of all matrices of rank strictly less than R. Okay, so this is not like a strange question to be asked. All right, let me give you $1 million example. You answer this question, you get $1 million. So now let's look at homogeneous polynomials of degree n on n by n matrices. Let's take as our group the group of all changes of bases in n squared variables. So this is not what we've been thinking about before. This is completely different. I'm forgetting that this is tensor product. I'm just allowing arbitrary changes of bases in that big vector space. I take my polynomial to be our favorite polynomial of all time, the determinant. I take, and I'm going to look at its orbit closure. And then I'm going to take another polynomial, the permanent. Unfortunately, it's not in the same number of variables. It's in fewer variables, the way I set it up. So let's multiply it by a linear form to the correct power so that it lives in the same space and has the same degree. So this is a homogeneous polynomial of degree n. It lives in this space now. And the question is this point in this orbit closure or in the boundary? Because it's certainly not in the orbit. And I haven't told you what n and m are, so this is actually a sequence of questions. As m grows, Valiant proved that if n is like 2 to the m, we know the answer is yes. And the question is, if n is like m to the 147, is the answer still yes? That's a variant of p versus np. If the answer is yes, you get $1 million cash, no questions asked. If the answer is no, you'll have to work a little harder because you'll also have to prove the theorem over finite fields. But this is one of the Millennium Prize problems. So this is a problem about an orbit closure. What lives in our orbit closure? Why is it interesting? Because if this answer is yes, that means you can solve the traveling salesman problem in polynomial time, and p is equal to np. If the answer is no, and you prove the same result over finite fields, then you can prove that you cannot solve the traveling salesman problem in polynomial. But it should be easier to solve over complex numbers. That's just my religious view. Any questions in the back? Am I going too fast today?
So the linear form is fixed, or you have to find a linear?
No, the linear form doesn't matter because I'm allowed arbitrary changes of bases. So all linear forms are the same. Other questions? Okay. So now you have an example that, it's clear that you get some money if you solve this one, but let's try the one that we were thinking about before. Let's go back to our situation. And we have our group of symmetries for tensors. And we look at our friend, the unit tensor, and we look at its orbit closure. And that is exactly the set of tensors of order rank at most m. Questions in the back? You kind of look amused. No, you're not amused. That's even worse. And last time, we motivated this question from matrix multiplication. And because we were looking for good tensors for the laser method. But I'm trying to say that this is also, you could forget about that and just think of this as an interesting question in algebraic geometry. In fact, I have a good friend who's a fairly well-known algebraic geometer / representation theorist, and well, I'll tell you the question I asked him actually in a minute. But before I do that, I want to do two things. I want to make one small comment, and I want to also explain motivation from quantum information theory. So, small comment. There's a classical theorem due to Matsushima that if not only is G reductive, but the stabilizer of V, the symmetry group of V, is also reductive, then the boundary is a pure codimension 1, which gives us a lot of extra information about what this thing looks like. So, and this applies to our case as we saw the group preserving, well, we saw the algebra of the group preserving the unit tensor is isomorphic to product of diagonal matrices in two spaces. So that's a reductive group. So Matsushima's theorem applies. So we don't know what our thing is, but we know that it's a union of irreducible varieties of codimension 1, which is a big help. There may be many components, though, but each component is a union of a family of orbit closures. So here are the questions we can ask in general. How many components are there? What's the geometry of a general element of the component? And when is a component itself an orbit closure? So now let me tell you some motivation from quantum information theory. So in classical information theory, we learned yesterday, there was these bits are our resource. And in quantum information theory, that gets translated to qubits, which are examples of tensors. Think of, in yesterday's talk, we had Alice and Bob, and maybe today we have Alice, Bob, and Charlie. And not all tensors are equivalent as resources. So people want to know if they have a tensor as a resource, something that they're physically building in a lab, according to Iacopa, how valuable is that tensor? So there's two aspects, the cost, which is like how much it costs to build in a lab, how much energy you have to use to construct your tensor, and value. How much classical information can it store, for example? And we want low cost and high value. And that exactly turns into asymptotic rank tells us the cost, because we want to build not just one copy, but many copies of our tensor. And asymptotic subrank tells us our value. So, so this is this whole business, if you've heard of LOCC and SLOCC, that's what I'm talking about. So that gives another motivation because now we're going to look at the things of minimal asymptotic, known to have minimal asymptotic rank, and then we want to have as much value as possible for our money. Okay, so let's go back to our classification problem. So if we just look at the orbit itself, that just changes the bases. So we just get tensors isomorphic to our original one. So we're really asking what's on the boundary. And there's sort of this irrelevant notion, irrelevant part of it, which is this non-concise locus. Namely, recall a tensor is concise if these three maps are injective, that is to say, if you need all your MQ, M, each vector space, you cannot stick your tensor in a smaller space. And if you can, then you should be working on a different problem, problems of tensors in this space. But today, I'm going to study in the other one. So I throw away those. Those are boring to me. Not boring, but not relevant for today. So this is the relevant part of the boundary. So this is a component of the boundary. This intersect, this is a component of the boundary. It's the one we're going to ignore today.
So sigma m is the matrix multiplication M1.
Sigma m is the tensors of order rank at most m.
Any possible order rank m, yeah.
And I'm saying that's an orbit closure. And so we can study it, its boundary. That's what we want to study, because the interior is just stuff isomorphic to what we know. So we want to know what's new. So this is known in small dimensions. There's nothing there at all when m equals 1. When m equals 2, there's a unique, the boundary consists of the orbit closure of a unique tensor, and it's one we saw yesterday, this so-called W state, otherwise known as a tangent vector to the Segre variety. So m equals 1, m equals 2, completely understood. M equals 3, it's also understood. There are two additional interesting things. So there's first, we could take the M1 direct sum W, because it has to be a 3-3-3 tensor. So this is a 2-2-2 tensor, this is a 1-1-1 tensor. You add them together, you get a 3-3-3 tensor. Then the next one, well, what is that? It's your homework. And then there's a third one. What is that? That's also your homework, but I'll tell you the answer. So you just have to prove that the second is, so this W is like x prime. I take a curve x of t, and I take x prime at 0, that gives me W. This mysterious one, I take a curve x of t, I take a general curve, I take x prime at 0 plus x double prime at 0, I get a tensor that looks like this, if I haven't made a mistake. Is that clear? So I have a curve x of t. If I take x of 0, I'm just going to get this unit tensor, 3 copies. If I take x prime at 0, I'll get something that looks like this maybe. And then if I take x double prime, well, x prime plus x double prime, I get something that looks like this. And in fact, the first 3 terms look like W, and the second 3 terms also look like W, but they're tied together.
But this is sum of the first and second division.
I'm saying this is the first, which we already knew about. The second one I can get by taking curve x of t and taking the limit as t goes to 0, and I take x prime of 0 plus x double prime of 0, and that will have border rank 3, and it will look like this after change of basis. The third one is even more interesting. So this Segre variety, if we picture it, this is the first example of the Segre variety. It's like a hyperbola, as you know, the hyperbola has lines on it, right? You learned this. And the Segre variety, the tensors of border rank 1, also have lines on them. In fact, they have larger linear spaces often. And so let's take 2 points on our Segre variety that are collinear. And let's look at the tangent space here and the tangent space here. They'll have a line in common, this line namely. And I take a generic tangent vector here and a generic tangent vector there. That's the third example. So this is like, these two are this is the most fun exercise. So I gave you an exercise sheet. If you're only going to do one exercise, you'll have the most fun doing this one. So it's a really pleasant exercise. So there's very simple geometric explanation of all these things when m is less than or equal to 3. Then n equals 4, we start losing geometric explanation, but at least we have complete classification. And note, still there's only finite number up to isomorphism. When m equals 5, there's still only a finite number up to isomorphism. And there was a sort of putative classification in the linear algebra literature, but it had some needed some fixing, and that fixing was accomplished last year. So our contribution was in this m equals 5 case in the well, I'll tell you later in the talk what was the important part of our contribution. I stop at what time?
You still have 1 hour.
Oh, so I stop at 1/4 Yeah? Okay. So I'll tell you about our classification later, but I want to tell you 2 consequences of it. One is that if m is less than or equal to 5, this interesting boundary has only one component. So I told you it's equidimensional, but it's only one component. It's irreducible variety. It's kind of amazing. And it's an orbit closure. Namely, the orbit closure that we saw already. We take this W and we add to it whatever we need to get an MMM tensor. We take all changes of bases of that, and then we close it up. And so when I started working on this problem, actually the question I asked the sort of rather well-known and deservedly so mathematician was, will this persist? If I go to higher dimensions, should I expect that the boundary will continue to be irreducible and an orbit closure? And well, I really wanted to know that. That's what started this project.
So who is this well-known celebrated mathematician?
Shravan Kumar. Yeah, see, he's really good mathematician. But it doesn't matter. I'm just saying that he had no idea either. So if I have no idea, it just means I'm ignorant. But if he has no idea, that means it's not known. That's the difference.
But I am confused. Before you said there was 36, and now you.
No, there were 36 things on the boundary up to isomorphism. But every single one of them lies inside this orbit closure.
All are in the closure of this.
Yes. Yes. So the boundary is an orbit closure. And it's, in fact, the orbits are nested. This is, so I take the orbit closure of this, and in fact, its boundary is an orbit closure. And then I take the boundary of that, that's also an orbit closure until I get down to nothing. It's really, it's like the Russian dolls. Everybody is nested inside everyone else. It's like a really ridiculously nice structure. But this persisted up until dimension 5. 5 is not a really small number. I mean, Well, depends how you think of it. But if you have a conjecture and it's true in the first 5 cases, you're feeling like you may be onto something, right?
Sorry, I have a question. So how this thing is stratified by multilinear arc? Is there any relation?
No. So this con throws away anything that is not a full multilinear rank. So yeah, so I'm throwing away.
But it's boundary.
Yes, but I don't care about that because because once I get out of that, I should be studying a different question.
Concise means maximum.
Maximum.
Maximum,
Because
yeah.
Today you were also mentioned this one agent.
That'll come later in the talk today. That's a more subtle property. Okay, so that's like really remarkable structure. And like I said, there are normal forms. Now we know that cannot persist just by dimension counting, that eventually there has to be moduli. But the question is, when do moduli first appear? And these were, so question is, well, the first question is, does the first n less than or equal to 5 result persist? It was not known whether that would be yes or no. We knew the second could not persist, but we didn't know how far out we had to go. Do we have to go to m equals 15 or 14? That's actually an important number because there's a phase transition at 14 and 15. So we don't know. We didn't, but the question is, so for the second, yeah, so obviously now you know what this talk is going to be about. It fails. And let's just cut to the chase. Already for 666 tensors, there's a component that is not the closure of a single orbit. In particular, that has moduli. So there's a non-trivial moduli space when m equals 6. And I'm even going to be able to describe the moduli space for you as follows. So a general point of this component looks like this. You pick a generic, say, 5-dimensional subspace of 3 by 3 matrices. All 5-dimensional subspaces work, but a general point of the boundary will be a general 5-dimensional subspace of 3 by 3 matrices. And you take the tensor such that the associated slices are the identity, and then these 5 slices from Z. So it's a 666 tensor. And so what is not at all, it's not so difficult to prove that this is a collection of minimal border rank tensors. What is more subtle to prove is that this actually gives a component of the boundary, that there's enough of these tensors to fill out a codimension 1 subset of our variety. So already the very next case, the world starts completely behaving differently. And that you get the whole component by taking the orbit closure under all changes of bases of such tensors. But a typical tensor looks like that. So it's not like, once I write it down, you're like, oh, sure. But how could we possibly have found this thing? That is crazy. I mean, and we found this thing literally I think this is certainly 2025, like February 2025 almost. Well, not February, but let's say it was before I got on the airplane, but not before I started packing.
Excuse me, I have a question on the dimension because Z has 3 times 3, 9 moduli. And so the dimension on the
No, Z has is a point in the Grassmannian of 5 planes, so it's 5 times 9 minus 5, which is 20.
Even worse. So I don't understand if it is concise, the image should have dimension 6. And
why would that? I don't understand. The image, yeah, because I have this identity matrix here. I have this and this.
Then there are two. Should
No.
have dimension 6.
I have 6 slices. This slice, which gives me identity, so that makes it B and C concise. And then I pick Z, since I pick my 5 matrices linearly independent, it's 8.
It was weekend. Sorry.
It's 8.
Now I understand. 5 plus 1 is 6. Okay. I
Good.
sorry.
I'm getting a little scared that the only person asking questions today is the world expert who's in the audience. No, I'm not scared that you're asking questions. I'm scared that you're the only one asking questions. Well, we're not asking you questions, so the 2 world experts in the audience.
So you have to ask questions.
Okay, let's just make sure we're all on the same page. We're looking for now 666 tensors of order rank 6 that were not previously known, and that we want them to be kind of closer to the unit tensor than Coppersmith-Vinograd in the sense that their asymptotic subrank is larger. And one way of doing that would be to be a general point in the boundary. And I've given you a list of general points in a new component of the boundary that did not exist in smaller dimensions. So this is a qualitatively different tensor than what exists in smaller dimensions in some sense.
Okay, here is a question of a trivial kind. How did you?
The rest of this talk is going to be dedicated to explaining that.
And what was the initial idea? Where were you going?
We're going to switch to the world of commutative algebra. And commutative algebra handed this thing to us.
Is it the only component? The only?
Yes,
component
this is, well, we have not proved that yet, but we strongly believe that this is the only new component in this dimension. I'll give you the landscape in a moment. Yeah, so this is what I said. There is something to prove. I mean, it's not so difficult to prove its minimal border rank, but it's a little bit more tricky to prove that it fills out a codimension 1 subvariety. That's a non-trivial calculation. We actually 3 different proofs of it, so I'm pretty sure it's true. All right, so now we got to explain where this is coming from. Right, so first of all, we have this classification problem, and I'm going to break it into 4 sub-problems. I don't know whether this will make my life better or worse, but they really are very different kinds of questions in nature. So remember that a tensor is 1A generic if there's a matrix, when we think of it as a space of matrices, there's a matrix of full rank in the alpha side, in the A. If you think of it as a space of matrices parameterized by A dual, there's a full rank matrix. Similarly, and we have 1B generic and 1C generic, then they'd be, so we have 3 spaces of matrices, and it's 1 generic if each of those spaces has a full rank matrix. Notice that's a open condition. So a random tensor will be 1 generic. Most tensors are 1 generic. Now, let's say, well, maybe it's not as good as 1 generic, but it's called binding. That's terminology to Blazer and Lysakov, who named it. If it's at least 2 of 1A and 1B generic, and let's call it strictly binding if exactly 2. And then it is 1 star generic if it's at least 1 of them, and strictly 1 star if exactly 1. And then the poor tensors that are 1 degenerate, that don't have any full rank matrix at all these things are contained in the 0 set of the determinant. And if you remember the discussion of Strawson's equations, they were almost worthless here because we wanted to use like T of alpha inverse to get our equations. And so if we don't have something invertible, we could still take the cofactor matrix. But for example, that's a rank 1 matrix, so commutator is not going to be that good for us. So these are the most mysterious ones. These are the easiest. This is like easiest, next easiest, next easiest, scary. So now we have 4 problems instead of 1. So we break it up into 4 problems. So, oh, by the way, so the classical component of the boundary is such that a general element is 1 generic. So that theorem also gave and this really surprised me. That theorem says that when you go 1 dimension higher to m equals 6, there's a component of the boundary whose general element is not 1 generic. So it's actually 1 star generic. It's like all the way down here, which really actually that's the most surprising thing so far in our study. But that's like kind of a surprise only an expert, only someone who's spent a lot of time thinking about it could love. But it was really kind of shocking to me that we jumped from here all the way down to here right away. It's very bizarre. So, like I said, I was surprised. I was also surprised that there was extra component, but I was only a little surprised. I thought of it, eventually you would expect an extra component, but the very next case, that was a little bit of a shock. So unfortunately, these don't appear to be good for the laser method, which is why I presented you an 888 tensor, not a 666 tensor, to beat up on Coppersmith vinaigrette. So we have a lot of work, a lot of explaining. I owe you a lot of explanation. So, oh yeah, and this big Coppersmith vinaigrette tensor is 1 generic. Now, we have this strange theorem we proved a few years ago that it's the worst 1 generic minimal border rank tensor for the laser method. In the following sense, that all 1 generic tensors degenerate to Coppersmith vinaigrette. So in particular, all 1 generic minimal border rank tensors degenerate to Coppersmith vinaigrette. So, yeah, it's a little depressing, right? But anyway.
Because the one that works is the worst one.
Yes, exactly. So when we proved this, for all we knew, this proves it's the worst, but we could have also ended up proving it was the best. But it turns out that's false by what I told you already, that there are tensors that have minimal border rank and less barrier. But that is only a few weeks old. Yeah, so that's what I'm saying. That's what I said already. The kind of idea is that if you have something that's a general component point of the boundary component, it might have higher asymptotic subrank. And as I mentioned, because someone asked about it, this unit tensor itself is useless for the laser method because of the structure, the combinatorial structure that people want for that method. Unit tensor, this one that's our benchmark, it sort of completely lacks the type of structure you need to use for the laser method. So, right, so now I want to describe a class of tensors of minimal border rank that's promising for the laser method that includes this one from, well, the beginning of today's lecture now. So I want to talk about binding tensors in general. So those are 1A and 1B generic, let's say. So when we consider a tensor as a bilinear map, we talked about that. If it's 1A and 1B generic, we get linear isomorphisms. I can identify B dual with C after a choice of alpha. After a choice of beta, I can identify A dual with C. So when I take the inverses, we can apply those to get an isomorphic tensor that just lives in the same space. That is a bilinear map from the vector space C cross itself to that. Well, a vector space equipped with a multiplication is called an algebra. And any Yeah, it need not be abelian or even associative, but it is an algebra. So any binding tensor is an algebra, is isomorphic to the structure tensor of an algebra. So this has nothing to do with minimal border rank. So if I'm binding, or even better, one generic, I get an algebra. And now we can sort of change gears and forget about tensors and just try to classify algebras, but algebras with additional condition that comes from being minimal border rank. So this is just algebra, and now we want what's nice about our algebra in the sense that its structure tensor has minimal border rank.
So it's not associated.
In general, no. Yeah. So it's just a mess. It's garbage. But don't leave the room in a haste, because if we have Straussen's equations, then remember we got this abelian space, and this gives us actually an algebra that is both abelian and associative. So if we insist that our tensor that has the mild genericity condition of being binding and satisfies Straussen's equations, then the algebra structure we get is abelian and associative. So it's a nice algebra. And in fact, we can explicitly describe it as the quotient of a polynomial ring by an ideal. And the zero set of that ideal should be an m-dimensional, the algebra itself is m-dimensional. So the zero set of the ideal will either be like m points, or if in the language of schemes, a zero-dimensional scheme of length m. All right, so now we have an algebra that's a polynomial ring quotiented by an ideal. But what we want to know, that was just a necessary condition to be minimal border rank. We want to know how far is that from being sufficient. So now we can translate that to a property of our algebra. So our tensor has minimal border rank if and only if this algebra is smoothable. That is to say, a limit of algebras that are direct sums of n copies of the trivial one-dimensional algebra. Now there's a problem here.
What is the topology?
Exactly. What do I mean by a limit? Because, well, I can think of, I have a curve of ideals, but where do I take my curve? Ideal is an infinite dimensional object, right? It's in all degrees. How am I going to keep that under control? Well, here's where we get really lucky. This problem was solved in the 20th century. There's something called the Hilbert scheme that exists exactly to parameterize ideals. And the answer, the good news is we've reduced it to a question that was well studied in the 20th century. This problem of which binding tensors satisfy Straussen's equations are actually minimal border rank is equivalent to something that was well studied in the 20th century. Unfortunately, unfortunately, we don't understand that much about it. It was well studied, but not well understood. But there are things that are understood. For example, you win. M less than or equal to 7, everyone wins. As soon as you have binding and Straussen's equations, your algebra is smoothable, and therefore any binding tensor where m is less than or equal to 7, we've completely characterized when they have minimal border rank. So that's victory. That's like a lot of hard work of other people, and but that's great. Now, the next component we found, we had to go up to 10. And we found a component when m equals 10 of this form, where now I use fancier letters, but it's still S mod I. Let's not worry about this because I'm going to run out of time today. And I think our time would be better spent discussing other things. But for the experts, here's the first example of a strictly binding component of the boundary. And this is the second example we're aware of. That's new. Of course, you can propagate the m equals 6 example I already showed you. You can boost it. But this is the first qualitatively new one we're aware of beyond m equals 6. And this talk is being presented in reverse historical order, in that the m equals 6 one was the last one we discovered just extremely recently. This one we discovered a few weeks earlier, and then there's another one that we discovered even earlier than that.
The quadratic equations, they are related to the commutation.
No, this is just this is just the smallest example. So this is the smallest example where you get enough minimal border rank binding tensors to fill out an entire component of the boundary. So of course there were strictly binding minimal border rank tensors in the lower dimension, but they were far from the surface. They were far from the interior. Here, you get an entire component of the boundary where every element is strictly binding. Previously, the only thing that was known was components where the general element was one generic, which actually I expected to persist, but it didn't. And this is the first violation of that we discovered. Right. So, so now let's sort of drop structure. Let's say we're not so lucky to have binding, and we only have one A generic, but not one B or one C generic. Well, we still have these Strawson's equations are non-trivial, and we get this abelian subspace of the space of endomorphisms of C. And we can upgrade that as follows. We can give that subspace the structure of a module over the polynomial ring. So why would I want to do that? Because we have a perfectly good space of commuting matrices. Why can't I just study directly whether this space of commuting matrices is limit of diagonalizable? Well, we don't know how to do that. So what we're going to do is we're going to stand on the shoulders of others, just like in the previous case, is we're going to try and reduce the problem to something that's already been studied in algebraic geometry. That's what I did in the previous page. With the binding case, we rephrased the conditions we knew in the language of algebraic geometry, and we were with a well-studied problem, and so we could just piggyback on the results of that well-studied problem. So I want to try to do the same thing here. I want to have some structure that looks like it comes from algebraic geometry. So now we think of our polynomial ring, and we can make our polynomial ring act on the vector space C because these matrices commute. I can upgrade this to an action of the polynomial ring because polynomials, you have to be able to commute. So I just have the variable yj on the vector C like this matrix. And since yijc equals yjic, because Strawson's equations are satisfied, I can upgrade that to an arbitrary polynomial acting on the vector space C. That is to say, our vector space C is now a module for the ring of polynomials acting on it. And now we can ask ourselves the same question: when is our module the limit of sort of trivial modules? That is to say, T has, in this situation, our tensor has minimal border rank if and only if this module lies in the smoothable component of the corresponding quote scheme. I was going to take half an hour to explain to you what that is, but we don't have that half hour. So I still have debts to pay, so let me pay my debts instead. But for those of you who know what the quote scheme is, or those of you who don't, just there's this object to parameter that when I do a translation, I get to a well-studied problem in algebraic geometry, perhaps not so well understood though. Questions?
How these translations work? Like, how can you express like the property of having minimal rank, minimal border rank, in a property of the algebra? Or
so a tensor has minimal border rank if and only if I take a curve of tensors isomorphic to this, and I get my tensor in the limit as t goes to 0. We had an example of that yesterday with the W vector. It had minimal border rank, but not minimal rank. It was a limit of a tensor that looked like that, okay? Now, I could translate this to a module, but the module will have a stupid structure. It'll just be the diagonal matrices acting on my vector space. But that's okay, because at each time t, I have a different incarnation of that. And if I know how to take limits of curves of modules, which is a problem they solved for us 75 years ago, then I could talk about taking limits of curves of modules. And then these people worked on that problem exactly. They found a space to study the limiting, and they've found tests to see if something is smoothable in their language. So it's because I have this curve of tensors, and that gives me a curve of modules. And then I use existing results from algebraic geometry. Other questions? Good question.
Like, I guess you talked about tensors of minimal border rank, but you can, if you take binding tensor, then you can still define this algebra. And what you can say, looking at the corresponding algebra, maybe in terms of.
No, it's arbitrary. Binding alone is arbitrary algebra. No, the question is
about the border rank.
Binding plus Strawson's equations, you get that the algebra is at least commutative and associative. And with unit.
Can you infer something about border rank?
Nothing at all. No, because a random tensor, you get some random algebra with no further structure, not abelian, not commutative, nothing. But we don't have a random tensor. We have a tensor satisfying Strawson's equation. And then we start getting structure. Other questions? Any in the back? Yeah, and if we actually had something that was binding to begin with, we would still get a module structure, and the module structure would say it's, well, anyway. Right, now, by binding, we have an algebra structure, but what if we're one generic, not just binding, but one generic? We should not have a arbitrary class of algebras. And I was very happy to hear the word come up earlier in the week. So I could just put it on the board. We get something additional if we have this extra structure to our tensor. What do we get? We get a Gornstein algebra. And Gornstein algebras have also been studied more recently. We know that very much more recently, all Gornstein algebras are smoothable when m is less than or equal to 13. So for free, if we have one generic tensor that satisfies Strawson's equations, it's automatically a minimal border rank. Absolutely free, no work on our part. We had to just do the translation. Oh yeah, what is the Gorenstein algebra? Yeah. Well, I guess we have to do it. Yeah. So so we're only dealing with finite dimensional Gorenstein algebras. So let me switch gears a little bit. Let's say I have a polynomial of degree d that uses all my variables. I define the annihilator of the polynomial. We saw this earlier in the week. These are all the differential operators that kill our polynomial. It's played a role in several lectures. And yeah, like we discussed, the action of the dual polynomial ring is just by differentiation. So in particular, if I take too many derivatives, I always get 0, so I'm always in the annihilator. And in the critical degree, the annihilator is a hyperplane. Now, we define the apolar algebra of our polynomial to be all polynomials quotiented by the annihilator. This is a graded algebra, even if our original polynomial was not homogeneous. It was this differential operator. We know what its order is. And apolar algebras are the local Artinian Gorenstein algebras. So these are our heroes. All finite dimensional Gorenstein algebras are just direct sums of apolar algebras. Let's see. All right. So you can, I just quickly explain how to get the Coppersmith-Vinograd tensor from this construction. So I'm going to take a degree 2 homogeneous polynomial, quadric, and I take its apolar algebra. So it'll have one element in degree 1. It'll have q elements in degree, one element in degree 0, q elements in degree 1, and one element in degree 2, because this sim2v star killing the thing, well, the annihilator was a hyperplane, so when we quotient, we get a one-dimensional object, and that's this degree 2 thing. So very simple structure, and in this algebra, the only interesting multiplication is when we multiply these, we get, since it's sum of squares, this multiplication is 0 unless I equals j. And if we choose the names of our variables carefully, then we get Coppersmith-Vinograd tensor back. Okay, this is just an illustration. So it's not particularly mysterious operation. It is a little annoying because you have to take equivalence classes, but that's life. Right, so this Coppersmith-Vinograd tensor is the structure tensor of the apolar algebra of a smooth quadric in Q variables. And so hence indexing it by Q is not so bad after all, although Coppersmith-Vinograd certainly did not know about this. So now I can tell you what this better tensor we have is. It's the structure tensor of the apolar algebra to the cubic polynomial x, y, z. If we consider this cubic polynomial as a tensor, it turns out before the big Coppersmith-Vinograd tensor, there was something called the little Coppersmith-Vinograd tensor. And the littlest little Coppersmith-Vinograd tensor is isomorphic to this polynomial. And the little Coppersmith-Vinograd tensor is one of the few tensors we know that's unobstructed, that has no barrier in Strawson's laser method. Unfortunately, it's not a minimal border rank, but what we got in T-better 6 is we somehow put it inside something bigger and constructed something a minimal border rank from this little one that's not a minimal border rank. And that blue corner, if you remember the beginning of the talk, is exactly the little Coppersmith-Vinograd tensor, the littlest little Coppersmith-Vinograd tensor, which potentially could be used to prove the exponent is 2. So it was very natural to look for it once we realized that cubic polynomials were a rich hunting ground. And in fact, this was the first thing we proved, that but notice it's in dimension 16, that in dimension 16, you get an entire component of the boundary by looking at structure tensors of apolar algebras to cubic polynomials in 7 variables. So 16 is 1 plus 7 plus 7 plus 1, because our apolar algebra has degree 0, 1, 2, and 3. And this was the first thing we found. And then once we realized this was fruitful, we said, well, let's look a little smaller. It may not give us a component of the boundary, but we know it should give us a good tensor. So finally, I hope this explains some of the mystery behind that new example. We first found this, which gave us a component of the boundary. Then we were very excited. And then we said, well, maybe we could find something a little smaller that's almost as good. That's how we did it. So here, general element of the component is one generic. And like I said, to be honest, I was surprised there are components of the boundary that are not one generic, generically. And this is the first M where we know of a component of the boundary that the general element is the structure tensor of an apolar algebra. So this is sort of we've been calling these kind of atomic tensors. So this is sort of the first atomic component of the boundary. So now we go to the disaster case where we have no structure at all. And I should go back. Is there any questions on this theorem? So this theorem is maybe boring after the first two. The first one was the most exciting one. And then now it's sort of, okay, larger dimension and less pathological. But somehow these ones are giving us good things for the original motivation of the problem, in the sense that these ones really look like they're going to beat Coppersmith vinaigrette, as opposed to the other ones.
Here you have symmetric tensors.
Any one generic tensor satisfying Strawson's equations is automatically symmetric. That's a theorem. I don't know who that's due to. I think that's also maybe Blazer Lysakov. I don't know, but that's been known for a while.
But you prefer to work with them as proof.
Well, because I want to treat all 4 cases at once in some sense and go back and forth. And those are the only ones that are symmetric. Okay, so Friedland. So in some sense, like people used to make fun of me, and well, they still make fun of me in algebraic geometry because I don't like to use this heavy modern machinery. And one time, someone actually sang the song John Henry for me when I was trying to prove a theorem without using some machinery. And so Friedland is someone after my own heart. He does the most with the least technology. So he salvaged something from Strawson's equations, even in the one degenerate case, and he used it to prove that when m is less than or equal to 4, there's no one degenerate minimal border rank tensors. And that's basically how the classification in the m equals 4 case was finished, thanks to his work.
Sorry, this was the paper by Shmuel on the salmon problem.
Yeah, the same paper. And then after that, there was no further progress because there was no extra structure to hang on to. So there was no way to test if a one degenerate tensor was minimal border, right? And then this 1-1-1 test came, and it gave us an extra necessary condition, but it still was not sufficient. So we have this necessary condition that is, the way I phrase it is due to us, but it's actually due to Baczynski family when we just say it without the algebra structure. but then it has to be smoothable as an algebra. So this is a theorem that is not entirely obvious in the sense that this 1-1-1 algebra is not obviously connected to our original tensor. So there's no obvious way to sort of take a curve of tensors here and get a curve of 1-1-1 algebras in the way I described, because there's no natural parameter space. So there's something to prove here. And then we have modules, but we still have quote scheme for those 3 modules. So, and we don't know if this is sufficient, but in any case, these 2 sentences here is what enabled the m=5 classification to go forward to deal with this previously mysterious case of tensors that almost did not have any structure. So it was a lot harder. Yeah, so that's what I just said. Okay, so we still don't know if there's a component of the boundary with the general element is this kind of super pathological 1 degenerate case. And I went way too fast, so you'll have plenty of time for questions or coffee as you play this. And I thank you for your attention.
So, question.
I have a more general question. So, these tensors, finding these better tensors just shows that the omega constant is lower, right? So that
No, we have not shown that.
okay, you have to, but yeah,
We hope to show that.
yeah, I mean, like,
So the point is that there's this world champion, and then there's a theorem saying game over for your world champion. And now we have another tensor that is at least as good as the world champion that the theorem does not apply to. But we have not yet, so there's this whole component of the laser method involving probability. And I'm not a probabilist or a combinatorist, which is the other aspect of it. But there are computer scientists who are effectively probabilists and combinatorists, and we're hoping that they will take this tensor and do their magical stuff and do it, you know. So that's where things are at. But you're getting a very sort of hot off the presses. This part of the talk is like hot off the presses, brand new stuff. Like I said, really just a few weeks old. So we don't know yet. I mean, a year may go by and then we'll be all depressed that, oh, nothing's, and then we'll start trying to prove that nothing is going to do better with this method, that the method is dead. But now we're kind of excited. We think the method will go a little further.
maybe a follow-up question then, maybe. Is there any hope of actually extracting the algorithm out of these probabilistic methods? No. Okay.
Absolutely not. There is a whole bunch of other, I mean, we have so little time together. There is a huge group of people trying to come up with practical things. So by the way, if you're not doing anything next fall and you're still willing to travel to the US, which is not true of some of my collaborators, and I don't blame them, we'll be having an entire semester on matrix multiplication and related problems at the Simons Institute for Theoretical Computing in the fall at UC Berkeley, and you're all welcome to come. We'd love to see you there. It'll be a quite interesting mix of people. And in addition to these asymptotic questions, one of the big questions we'll be working on are practical algorithms.
So is it the case that with every tensor you get a Artinian constant?
No, every one generic tensor that satisfies Strawson's equations. So there's a genericity condition, this one generic, and then there's a closed condition satisfying this polynomials defined by Strawson.
And if these algebras are isomorphic, this is like
If the algebras are isomorphic, the tensors are isomorphic. The algebra is smoothable, the tensor is minimal border rank. So there's a complete dictionary.
so
And in fact, if you know some algebraic geometry, in this paper that we're writing, we prove like something very, very strong, that you take any natural geometric set on the algebra side, and you have a natural geometric set on the tensor side, and those two sets are smoothly equivalent, which is a brand new term for me, which I didn't know until I was working on this project. But it's great when you work on a new project and you become a student again, because learning all this new algebraic geometry.
More questions? So can you explain again this where this your newborn tensor is situated? Sigma 8. You said that you mentioned something called, so it's like on which tensor?
Well, yeah. So we have sort of these two ingredients here. We have these apolar algebras of cubics. And we saw when we're, well, cubics say in 7 variables, then we get n equals 16, we get a boundary. If we're in fewer variables, we still get minimal border rank tensors. And the minimal border rank tensors will have this structure that looks like this. So the blue we think of as a Coppersmith-Vinograd tensor. And then we get to add in what actually we proved. This was not at all obvious in the beginning, but we proved it. If you choose your bases right, we get to add in something red that is actually just the original cubic polynomial expressed as a tensor. But the point is when we're in 7 or fewer variables, we can add to this tensor, which is the current world champion in its dimension, a red splotch at no extra cost. So I should explain that this big Coppersmith-Vinograd tensor is actually this little Coppersmith-Vinograd tensor plus this A0, B0, CQ plus 1 plus A0, BQ plus 1, C0 plus AQ plus 1, B0, C0. And the way they found this is they realized they could start with this, which was in 1987, the world champion. They could add this in at no extra cost. This thing and this thing have the same border rank. So we're really doing what Coppersmith-Vinograd did to their own tensor. They started out with their small tensor and they said, oh, we can add this in at no cost. It's certainly not going to hurt us. And then they got this and it turned out to do better. And that's what we have. We have this blue one, we have their hardware, and we get to add in the red splotch of our choice at no extra cost. So then we say, well, what red splotches should we add in? Well, why don't we add in something corresponding to that? Because that's free, and that's known to be good.
Like geometrically, like you have this component. I didn't get
Right. So there's the theoretical question in geometry. Understand the components of the boundary, and then our first discovery was that there's a component of the boundary coming from cubics in 7 variables. We uncorked champagne. We were delighted, and then we said, well, these should be good for laser method. And then we did not know how to write these down as tensors in a nice way. We spent a few months and we realized, oh, if you write it as a tensor in the right way, it looks like this. And they say, oh, but it's copper-Smith integral plus a red splotch. And we're like, oh, this is great. Now we just have to look for good red splotches. So you're really getting this as we're discovering it, right? So we had this component. So historically, we had this component, answers a geometric problem. There are other components of the boundary with moduli, which we didn't know about before. And then we say, let's think about laser method. And if you think about laser method, well, let's put this in a nice form. And then when we put it in a nice form, we realize, oh my goodness, that's copper-Smith vinaigrette plus a red splotch. Yeah, so that's where we're at.
More questions? So if not, we can, oh, this one.
So can you describe effectively how you associate the algebra, this answer in your side?
Right, so it's easier to go from the algebra to the tensor.
Yeah, but even the tensor, how you get the
No, from the tensor, we know there exists an algebra. There's a theorem, there's an existence theorem that says it must come. Gorenstein algebra has a structure theorem, and we know we have a Gorenstein algebra. We don't know. We don't know an algorithm to do it yet. So in the cubic case, we did because we found a nice way to write them down, and then it became obvious. But if we go to degree 4 polynomials instead of degree 3, and then we look at a tensor to write that as structure tensor of some apolar algebra, and, and we don't know it's a degree 4 polynomial. We just know it's Gorenstein, that polynomial of some degree in some dimension. And so here we kind of got lucky because we have this nice structure theorem. And already when you look at 4, because in 4 you have this extra flattening, the 2-2 flattening, and then you have to study based on the rank of that 2-2 flattening. I mean, if you assume it's maximal rank, that's the easiest case, and mathematically. But there's all these other cases around there. It gets pretty scary pretty fast to go from tensor to algebra because there may not be a unique way to write down the algebra. There is not a unique way, but there may not even be a structurally unique way to write down the algebra.
Good. No more questions, so we can thank GM and good office.